Our sun, a blazing sphere of plasma that dictates life as we know it. This massive ball of gas, primarily composed of hydrogen and helium, is the very heart of our solar system. It provides the light and warmth that allows life to flourish on our planet. Without its radiant energy, Earth would be a frozen, lifeless rock drifting through space. But the sun is not always a benevolent neighbor. Its surface is a cauldron of continuous nuclear reactions, and sometimes it can be quite unpredictable. It can unleash powerful bursts of energy, reminding us of its awesome power. These solar flares and coronal mass ejections can have profound effects on our planet. On May 14, 2025, an X2.7- class solar flare erupted from the sun's surface. This was one of the most powerful flares recorded in recent years. This event served as a potent reminder of our star's volatile nature. The sun's surface is dotted with sunspots, regions of intense magnetic activity. The flare, originating from a cluster of sunspots, sent a surge of radiation hurtling towards Earth. This radiation travels at the speed of light, reaching our planet in just over 8 minutes. Fortunately, our planet's magnetic field and atmosphere absorb the brunt of this energy. These natural shields protect us from the sun's more harmful emissions. However, the event did not pass by completely unnoticed. The surge of energy caused disturbances in the upper atmosphere, affecting communication and navigation systems. Reports of radio blackouts and disruptions to GPS systems surfaced, highlighting the tangible impacts of such solar events. These disruptions can affect everything from airline navigation to emergency services. The May 14th flare was a significant event, but it was not an isolated one. Solar activity follows an approximately 11-year cycle, with periods of high and low activity. It was part of a pattern of increased solar activity that has been observed in recent years. Scientists have been closely monitoring these changes to better understand the sun's behavior. These events serve as a stark reminder of our planet's vulnerability to the sun's whims. The delicate balance between receiving life-giving energy and being exposed to potentially harmful radiation is a constant dance. Understanding these solar events, their potential impact, and how we can prepare for them is no longer a matter of scientific curiosity, it's a matter of societal resilience. Preparing for solar storms involves safeguarding our technology and infrastructure. As we delve deeper into the realm of solar activity, it's crucial to appreciate the delicate balance we strike with our star. Our very existence depends on this balance, and our future may hinge on our ability to maintain it. The sun, the giver of life, also possesses the power to disrupt the very technologies and systems we rely upon. From satellites to power grids, our modern world is intricately linked to the sun's behavior. This dichotomy underscores the importance of unraveling the mysteries of the sun and learning to live in harmony with its dynamic nature. By studying the sun, we not only learn about our star but also about the very forces that shape our existence. Imagine 1 billion atomic bombs detonating simultaneously. That's the raw energy released by an X-class solar flare. These are the most powerful explosions our sun can produce. They are classified by their X-ray intensity, with each letter representing a 10-fold increase in energy output. An X2.7- class flare, like the one we experienced, is a force to be reckoned with. The intense radiation can penetrate Earth's upper atmosphere, disrupting radio communication and navigation systems. Astronauts on the International Space Station are particularly vulnerable during these events and must take shelter in shielded compartments. Solar flares can also trigger geomagnetic storms. These occur when the sun launches a coronal mass ejection, a giant cloud of magnetized plasma, towards Earth. When a CME interacts with our planet's magnetic field, it can induce powerful electrical currents in power grids, potentially causing widespread blackouts. These are not mere hypothetical scenarios. In 1989, a powerful geomagnetic storm caused by a solar flare knocked out power to millions of people in Quebec, Canada. The economic impact of such events can be enormous. More recently, in February 2022, a geomagnetic storm caused by a CME destroyed 40 newly launched SpaceX Starlink satellites. The year 2024 was a particularly active year for our sun, marked by an unprecedented series of solar events that captured the attention of scientists and the general public alike. Multiple X-class solar flares erupted, sending shockwaves through the scientific community and raising concerns about potential impacts on Earth. These powerful bursts of radiation were closely monitored, as they have the potential to disrupt satellite communications, power grids, and even pose risks to astronauts in space. While most of these flares did not directly impact our planet, they served as a stark reminder of the sun's unpredictable nature. The sheer energy released during these events is a testament to the dynamic and often volatile behavior of our closest star. One notable event occurred in January 2024 when an X1.9- class flare erupted from a sunspot region on the Sun's eastern limb. This flare was particularly significant due to its intensity and the potential threat it posed as the sunspot region rotated. This region, facing away from Earth at the time, rotated into our planet's line of sight a few days later. The anticipation of a potential Earth-directed flare was palpable, with scientists and space weather enthusiasts closely monitoring the situation. The anticipation of a potential Earth-directed flare was palpable, highlighting the constant vigilance required in monitoring solar activity. Solar observatories around the world were on high alert, ready to capture and analyze any significant solar events. Another significant event unfolded in September 2024, when an X4.5- class flare, one of the most powerful in recent years, erupted from a sunspot group near the Sun's central meridian. This flare was a stark reminder of the Sun's immense power and the potential consequences of its activity. This flare was accompanied by a coronal mass ejection, which fortunately missed Earth. However, the event underscored the importance of monitoring these solar phenomena, as a direct hit could have significant impacts on our technological infrastructure. However, the event caused widespread radio blackouts and auroral displays across high-latitude regions. These stunning light shows, while beautiful, are a visible reminder of the Sun's influence on our planet. These events, along with numerous smaller flares and CMEs, underscore the heightened activity of the Sun in recent times. Each event, no matter how small, contributes to our understanding of solar dynamics and helps improve our predictive models. This surge in activity is not unexpected, it's part of the Sun's natural cycle. The Sun goes through periods of increased and decreased activity, known as the solar cycle, which lasts about 11 years. However, the intensity of some of these events has caught the attention of scientists and has led to increased efforts to better understand and predict solar activity. By studying these powerful solar events, researchers hope to develop better forecasting tools to protect our technology and infrastructure from future solar storms. The Sun is not a static entity, it is a dynamic, ever-changing star that plays a crucial role in our solar system. It pulsates with a rhythmic cycle of activity that lasts approximately 11 years, a phenomenon that has fascinated scientists for centuries. This cycle, known as the solar cycle, is characterized by periods of heightened activity, marked by increased sunspots, which are dark patches on the Sun's surface caused by magnetic activity. During these periods, we also observe more frequent solar flares and coronal mass ejections, or CMEs, which are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. These active phases are followed by periods of relative calm, where the Sun's surface appears more stable and less turbulent. We are currently transitioning into Solar Cycle 25, which began in December 2019. This new cycle brings with it a fresh wave of solar phenomena to study and understand. Solar Cycle 25 is predicted to be a relatively strong cycle, with scientists anticipating a significant increase in solar activity. The peak of this activity is expected to occur around 2025, a time when we can expect to see more frequent and intense solar events. This means that in the coming years, we will likely witness an uptick in solar flares, sunspots, and potentially disruptive solar storms. Understanding the solar cycle is crucial for predicting and mitigating the impacts of space weather, which can affect everything from satellite communications to power grids on Earth. By studying past cycles, scientists can develop models to forecast solar activity with greater accuracy and provide early warnings of potential threats. These early warnings are essential for preparing and protecting our technological infrastructure from the adverse effects of solar storms. This information is also vital for safeguarding satellites, which are crucial for communication, navigation, and weather forecasting. Additionally, it ensures the safety of astronauts in space, who rely on accurate space weather forecasts to avoid harmful radiation exposure. As we enter the peak of Solar Cycle 25, the importance of space weather forecasting and mitigation strategies cannot be overstated. These strategies are essential for minimizing the risks associated with increased solar activity and ensuring the resilience of our technological systems. The Sun's influence on our planet is profound, affecting everything from climate patterns to technological systems. Understanding its rhythms is key to ensuring our continued well-being in the technological age, as we become increasingly dependent on technology that is vulnerable to solar activity.